When reading phylogenies, it's critical that we read them based on the clades. And a clade is a group of organisms that all share a single common ancestor. So when we have a classification, which is simply a group of organisms that have all been put together and given a name, we want it to match our relationships. And originally, when classifications first began, and honestly they began the history of the human race, but they first began to be recorded and written down during the Greek philosophers, Aristotle, and then of course Linnaeus codified away with his taxonomy of us classifying and naming groups of organisms. But when that was done originally, we didn't understand this shared connection. We didn't understand the phylogenetic history. And there are some complications that can make it difficult to group organisms together. And in theory, we could group organisms together any way we wanted. We could do it by color. We could do it by, do they taste good? Where do they live? But other than being a system for grouping things together, it wouldn't have a deeper meaning. And so today we want our classifications to match the deeper meaning of the shared evolutionary history of species. So for instance, Aristotle, when he first began to classify organisms, he classified them into animals into four main groups. He said they're the animals that can fly, they're the animals that live in the ocean, there are the animals that dig underground, and then there are the animals that are terrestrial, that walk around on land. Now, obviously, this form of classification poses some problems. You would put birds and bats and flying insects all in the same group, whereas you would put crawling insects and humans and mammals all into another group. And so obviously this, although it is a system, and maybe even you could say we could objectively do it, it's not going to represent anything meaningful or deeper other than the system itself. However, if we group things based on their shared evolutionary history, then we have a non-trivial system of classification. Now notice you might also have jumped to the next step that there are some other problems. Maybe Aristotle's method was not as objective as we might have thought, because where do you put frogs, for instance? Some of them live on land and never go in the water except to lay eggs, and some even don't even need to do that. In the rainforest, it's wet enough they can lay their eggs on the underside of leaves. Right? So do you put a frog with the aquatic organisms, or do you put it with the terrestrial organisms? So some systems are maybe not as objective as we would like. And certainly we don't want just subjectivity where people group things together however they would like to do it. So our system of objectivity is the historical relationships. And so inevitably, as we begin to understand phylogenies and the evolutionary history of groups together, we needed to revise some of our classifications. So by definition, the only valid classification is a monophyletic group, or a clade. So we could put A and B into one group, say it's a genus, and give it a name, and it would be valid because A and B share a common ancestor, represented by that node right there, and we haven't left out any of the descendants from the common ancestor, at least based on this phylogeny. Okay? So a monophyletic group is a clade that includes all of the descendants from a single common ancestor. That's the easiest, simplest way to think about it. So A and B would be valid. C, D, and E together would all be valid because we can make a monophyletic group descended from that ancestor without leaving out any descendants. Now, obviously, I couldn't put B and C together and call that a group, give that a name, because if I did that, their common ancestor, which is at the root of the tree, and we'd leave out A, D, and E, many of the descendants of that common ancestor. So monophyletic groups are the only valid classifications, and as we have understood our history of species better and better, we've revised many of the historical classifications, and we'll give you some examples here in a little bit. And so we have decided that our taxonomy and classifications should agree with our understanding of phylogenies, and if they don't, they need to be revised. Now, if a brand new phylogeny comes out that contradicts an older one, we might want to wait a little while, see how well supported it is, see if further analyses also support that. So it's not an immediate revision as soon as someone comes out with the next best phylogeny. Sometimes there needs to be a preponderance of evidence, more and more consensus that yes, we're starting to understand and have very, very good support for the phylogenetic relationships. So many of our historical relationships, and some still today, are paraphyletic. Paraphyletic occurs when we have a group of organisms that are all classified into one group, say Reptilia, but we left out one of the descendants. So originally, the way Reptilia, they put it in quotes here because this is an invalid classification, but the way it was originally classified was lizards. We could throw in turtles and snakes and other groups, but these are, again, just a synopsis of members of the group. We've put these three together, but notice that we have left out, once we understand the true relationships, we've left out one of the descendants of this common ancestor of Reptilia. So it's a paraphyletic grouping that is invalid. And so we modify it. Now, how did we fix this quote-unquote bad Reptilia? Well, Reptilia sometimes does not use their other terms, but one way that we could do it is simply recognize birds as a member of the group Reptilia. And that's actually how this was resolved. Today we recognize that birds are Reptilia. Not only are they Reptilia, but they are also dinosaurs, because some dinosaurs, the theropod dinosaurs, including T-Rex, are more closely related to the birds than the rest of the dinosaurs. So if I put in another group for, let's say, Stegosaurus would connect in right there with that branch, and it would come out to right there. So to modify and recognize our classification, we need to include the group that was left out from this paraphyletic classification. So today, if we go back to the treeoflife.web or treeoflifeweb.org, if you go back there, you'll see that birds are included in this group. They are more closely related to dinosaurs than they are to the rest of the reptiles. In fact, they are dinosaurs. They are more closely related to crocodilians than they are to lizards, and they are included in a group with crocodilians and pterosaurs and all the other dinosaurs as a group that we call archosaurs. And we're not going to spend a lot of time in that for that class, but just recognize that. There are many, many other classifications that were originally paraphyletic. So the group fish, for instance, if you include the cartilaginous fishes and all the bony fishes and the lobed fin fishes, that is a bad group because the tetrapod vertebrates, right? So we've only got one fish here, but if I put in sharks, which we classify as fish, right, they would come out right here. If we put in the lobed fin fishes, they would come out as right there. So once we sample enough taxa, it's clear that the group that we call quote-unquote fish is a paraphyletic group. So we either need to include the tetrapod vertebrates as part of that group, or we need to revise and give new names. And either will work. Oftentimes, the excluded groups are simply then just folded in and included in the original paraphyletic group, making it monophyletic, or we revise and give new names to different groups. So paraphyletic groups are not valid and need to be revised once we understand and have good support for their paraphyly. Another form of non-monophyletic classification is polyphyletic. And polyphyletic groups are not valid also. So the answer to this is no. And in some ways, they're even worse than paraphyletic groupings because we have left out not only one descendant, but more than one. So in this case, if we're going to group all of these birds together and call them raptors, you know, the phylogeny shows our current understanding fairly well supported about these relationships. We can't call them raptors because we have left out the kingfishers, we've left out the parrots, and all of the passiform birds, which are this very, very incredibly large group. And so we can't call these guys raptors and put them in one group. Not only that, but it's not on this diagram, but some of the groups that were originally included as vultures, the New World vultures, condors, the black vultures we see flying around South Texas, it turns out that when we look very closely at all of their characteristics, although they are superficially similar to these Old World vultures, they're actually more closely related to storks and would be part of this group, the other ones. So anyway, this group that we call raptors originally needs to be revised. And so we sometimes will still use these words loosely, but they're no longer a valid scientific name for a group. So there's no scientific raptors, although when people say raptors, we understand generally we mean the hunting birds. And so this brings up a question of, okay, why were these originally classifications made? What caused the scientists to misunderstand and group organisms together? And so realize that historically organisms were grouped based on similarity. And sometimes even very early on they were grouped on just one similarity and not looking at all of the other characteristics that an organism had. But even sometimes looking at lots of characteristics, it can be a little bit misleading. So let's jump back and talk about this. Why were birds not originally included in the Reptilia classification? And in this case, as in the case of many paraphyletic organizations, The birds were not recognized because they evolved a lot. Their ancestors looked very similar, and if we had included extinct lineages, it might be a little bit more apparent about all the transitional and changes that occurred along the bird lineage. So often when one group goes through rapid evolution and diverges from its ancestral group, it will look so different that it's not recognized as part of that ancestral group. So rapid and even a key innovation, which we'll talk about in a little bit, or a series of key innovations, can make one descendant from an ancestor look so different that it's not concluded originally. And then later, as we gather more data and do more in-depth analyses, including all characters, we will often then recognize what's going on and then have to fold that group into the larger group. Polyphyletic groups are often the result of convergent evolution, and that seems to be the case here. If an organism adapts to a meat-eating form of life, right, attack, kill, eat the meat, then that might cause convergence. Now this is interesting because, and we'll get into this maybe a little bit later, this is an important point. We don't know for sure, and we may need to look at fossil evidence or map characters onto this phylogeny. We don't know for sure whether this polyphyletic grouping was actually a grouping of convergence. Maybe a better explanation for why the raptors all eat meat is more like this, where we have changes in one lineage. Because kingfishers still eat meat. They're slightly different and have different beaks that handle it, right? They don't no longer have this curved hooked beak for ripping up meat. They have more like a spear-like beak. But they're meat eaters, and so we could infer that the evolution of eating meat occurred in the ancestor here, but then was lost in these descendants. And that actually is probably a more likely, although there might be some debate among ornithologists. So polyphyletic groups can come about either because of evolution, right, losses of ancestral characteristics, or because of convergent evolution. If I throw in the New World vultures, which I mentioned are more closely related to the storks way down here, then suddenly we have, oh yeah, that's convergence that is contributing to this misclassification, because the Old World vultures, which are much more similar, the New World vultures, which are much more similar to storks, have many similar features because they converge to this same ecological niche that the Old World vultures have. So polyphyletic groupings, and again, we've covered, a rapid evolution, innovation of new features. We've covered kind of what we think about it as a loss of a feature, a loss of a meat-eating characteristic, which you could, depending on how you look at it, might be the gain of a new feature of eating seeds, although that's probably similar to many of these ancestors. And so sometimes the terminology is a little bit tricky. But by rapid evolution, by convergence, or by loss of certain features, we can have trouble classifying organisms. But as we gather more data, especially genetic data, which is a huge treasure trove of data that can help us to recognize connections and relationships between organisms, we revise our phylogenies, and that then forces us to revise our classifications. And we're going to spend much of the rest of this unit talking about the methodologies of how we make these phylogenies and then how we use them in different applications, including how we use them to understand and revise our classifications. A key innovation is a new characteristic, a new feature, or maybe a series of features that means a group is going to be very, very successful. Flight, for instance, is often a key innovation. And so bats are the most diverse and widespread group of mammals, and that's almost certainly because they have evolved the ability to fly. Birds are the most diverse of all of the living reptiles, and even more diverse than many of the extinct versions were. And that's because they've evolved flight. The flying insects, that's one of maybe others, but that allowed insects to be so successful. And there are others than flight, and we can look at key innovations, but it's anything that makes a group very distinct and also especially very successful in terms of biodiversity. And key innovations often are a series or a single very important innovation that can be misleading a little bit if that causes that group to diverge and become different than its ancestors. So birds look so different from other reptiles and were not originally included in the historical classification Reptilia because of these many key innovations. Feathers were the first one, obviously. Flight, there are many, many others. Birds have become quite distinct from the other reptiles. Everything from hollow bones to a beak to a specialized respiratory system. If you're an ornithology expert, you can probably add to that list. Now, occasionally you will see a phylogeny that has more than one descendant branch coming from a node. And these can be here at the terminal branches, or they can be internally also. Anytime we have 3 branches or more that simultaneously diverge from a single node, it is termed a polytomy. So this just means we have no idea about relationships. We know they're all connected to each other at some ancestral point because they're all living organisms, but this means it has no information at all. I could take any 6 organisms on Earth, put them on any of these branches of the tree, and it would be technically correct because they would all have come from one common ancestor at some point. This one is more commonly what we will see where we know some of the relationships and can resolve them fairly well. We have good resolution for these, but we don't know among these 3 species. And of course, so far we've been looking at fully resolved trees. Now, there are 2 reasons why you might see a polytomy. And we don't get into the details of this, and at least I don't in my evolution class, so you probably are not aware of this. The main reason, most of the time when you see a polytomy, it means that we don't have enough data. So that polytomy represents insufficient data to make a decision about relationships just within this group of 3 species here. Okay, so that is called a soft polytomy, is we don't have enough data. So if we gathered more data, then we may be able to resolve it and come up with a final solution. Okay, so solution to a soft polytomy is gathering more data, reanalyzing the relationships, and then hopefully we will be able to resolve it. Okay, so if we don't have enough data, or actually we can actually sometimes also have conflicting data that leads to a polytomy. But the solution to that, how we can resolve a soft polytomy, is by gathering more data. Now, a hard polytomy is another thing, and this is a very difficult thing to fully prove and resolve. A hard polytomy means that we had essentially simultaneous divergence of more than 2 lineages from a single ancestral lineage. And that occurs, but is probably fairly rare. Most of the time when species diversify, they break into 2 subpopulations, and then maybe even very soon after that, one of those populations may break into a third, break off a third population. So hard polytomies represent a biological reality of simultaneous divergence of more than 2 lineages from a single ancestor. But it's hard to prove if that was really the case, or maybe we just gather more data. And so essentially we gather data and gather data and gather data until we are saying, well, I can't gather anymore, at least at this point we're done. So it might be a hard polytomy. In reality, disproving a hard polytomy is kind of like trying to prove a negative. And so we can gather more and more and more data and become relatively certain, but we're never 100% certain that it was a hard polytomy. And in reality, they are probably fairly rare. Now, we've talked already about cladograms and phylograms. In addition, I want to talk about 2 additional characteristics of phylogenies that will be important a little bit in later discussions. Additive trees is a property of phylograms, meaning that we can add up all of the changes along the branches, and that will tell us the changes that occurred going back to the root or to the common ancestor. So for instance, if we have changes and they're represented just by numbers here, 2 changes along that line, 4 changes along that line, that means that there were 6 distinct changes that went back before A gets back to its common ancestor, and then 2 changes that separate C from that common ancestor. So in reality, there are 8 changes that separate now species A and species C. So we can add up all of the changes along the connecting branches to tell us the genetic distances, or if these are morphological characters, the morphological changes and distances between organisms. So if A represents birds, we probably have many, many changes that we would map along this lineage leading to modern birds. Okay, so that is the property of additive trees. It's one of the properties of phylograms. Cladograms, of course, that doesn't apply to because the branch lengths are meaningless and we don't know how many changes occurred on a cladogram. An ultrametric tree is an additive tree with one additional constraint imposed upon it. And that is that there is a roughly, or maybe even if we're going to be very precise, there is an even rate of evolution. So notice here, we can have different rates of evolution along different descendant branches. So C didn't change as much, and that's represented with this branch not being as long. A changed more. An ultrametric tree imposes the additional constraint of changes occurring at a regular rate, and so all species will have evolved the same amount. We can still add up changes, but if we go from any ancestor to one of its descendants, we're going to have the same amount of evolution that's occurred along those descendant lineages. Okay? So be aware that ultrametric trees have that additional constraint. Now, in most phylogenies, and there will be exceptions, and we probably won't look at them in this class, the x-axis is not meaningful. It's simply whatever is convenient to separate out the species enough so that it's legible and readable. So the x-axis doesn't mean anything. Now, notice there's one additional thing with this ultrametric tree. If a rate of evolution, if we can say, every generation there are X number of mutations, X number of changes that are fixed in a population, then we could, and this comes in later when we talk about the molecular clock, we could use this genetic distance as an estimation of how much time has passed. So notice that they have time here, where here it's just amount of overall change. So ultrametric trees also allow us the possibility, and this is why people use them, allow us the possibility of inferring a not only genetic distance between species, but also a absolute time distance, or estimating how much time has passed since these species diverged. And so that can be very useful. Occasionally you will see unrooted trees, right? So we've already talked about this. The root represents the common ancestor of all of the species in the phylogeny, okay? But how do we know that that's where it is? Why wasn't the root here? And then we would have to redraw this. Okay, so the root represents the common ancestor. So here's an example. This is the exact same phylogeny as here, but unrooted. And we could put the root along any of these branches. But trying to decide that, we just don't randomly do it. We just don't just say, oh, I think it should go here. In our case, we actually put the root right on that branch. So notice if I draw a root off of that, then A and B are on one side, C and D and E are on the other side, and then everything else progresses. So that's where the root is. So how do we determine where the root is going to be? And this is a little bit tricky, and there's a little bit of redundancy or catch-22 here. So here is a unrooted phylogeny, and they've just numbered the branches. These are not lengths here. They're just simply trying to show you that there are 7 different branches where we could possibly root the tree. This is an unrooted tree of the primates, a higher group of primates, the Old World primates, and I think baboons are on here also. So this is, I forget the scientific name of it. It's not great apes. It's because the baboons are included also. But anyway, this is a group of species. Humans, chimpanzees, gorillas, orangutans, and baboons. And notice that there are 7 possible ways we could root this tree depending on which of the branches we root it on. So how do we figure out which of these 7 possibilities is the right one? And so the root down here, although they haven't drawn the line going down, it's where this bottom V is. Okay, which one is the correct one? By the way, it turns out that this one, root number 7, is actually the right one. But how do we know that? How do we analyze that? Okay, well, the method that we use is called the outgroup method. And this is where the catch-22 comes in. So we would pick some other primate that we know is not part of this group, and this is the catch-22. We don't know ahead of time until the analysis is done, but to do the analysis, we need to include an outgroup. And in fact, often what people will do is include multiple outgroups. They might include a primate and another group of mammals that is fairly closely related to primate, and then do the analysis, and then we root based on that outgroup, right? So if we throw in a spider monkey here, it would come out as the most closest relative to the baboon. And so that's how we would know that this is the proper rooting. And then other groups of mammals would be farther and farther out. And so the catch-22 is that we have to estimate, or maybe even you could say guess, hypothesize, about what is a close relative but not part of the group that we're studying. And so we're doing a little a priori, and then we might need to revise, and we could probably get closer outgroups as we do more and more analyses. So it's a little bit of an iterative or a cyclical process sometimes. So to determine the root of a tree, we use the outgroup method. We include a species or a group of species in the phylogeny that are closely related but not part of the group that we're interested in. Now, in order to find the best phylogeny, we would need maybe to evaluate multiple hypotheses. And we'll talk about some of the algorithms and the overview of this in the coming chapters. But I just want you to understand one other principle of phylogenies that is very, very critical and will come up again. This is the number of possible phylogenies that we have for any group. And I'm going to illustrate this. So let me draw, I'm going to bring up just a little bit of make a new folder here, and I'll draw a little bit. And this is a little bit clunky. It's hard for me sometimes to draw on the computers, but on the screen. But this will, I think, illustrate it for you. So let's say we have 2 species. I'm going to use the paintbrush here. All right, so we have species A and species B. Now, obviously, there's only one way that we can group those together. They have a common ancestor. We could put a root down here, right? So there's only one possible phylogeny for 2 species, okay? How many possible, and we'll use rooted phylogenies, because the answer is slightly different if they're unrooted. How many possible phylogenies are there for 3 species? So let's go back here and let's do 3 species. I'm going to do species A, B, and C. How many different phylogenies can you draw? If you want to pause the video and think about it, try and answer it, you can do that. So I can put relationships like this, right? Here's my root. B and C are most closely related. That's one possibility. I could also say, no, A and B are most closely related, with C being distantly related. That's a second possibility, and that's different than the first one I drew. Now, there's one other possibility, and I'm going to have to rearrange our things here. So let's put C right here and B right there. I can say, no, A and C are most closely related to one another, and B is only a distant relative. I made that branch a little long. So there are 3 different ways, okay? So let's come back here and let's say if I have 2 species, then there's only one phylogeny I can draw. If I have 3 species, then there are 3 different possible rooted phylogenies, okay? What if I include a 4th? Let's put a D in here. Now, this becomes a little trickier to illustrate, but one of the nice ways that you can think about this is, well, let's do an unrooted phylogeny. Oops, redo that. Sorry. There we go. Let's do an unrooted phylogeny for A, C, and B. So I'm going to simply move B here. Let's erase it, because if I undo, then I'm going to lose it. I need a bigger eraser. All right, so I'm going to put B right here. Pack my brush. And an unrooted phylogeny would simply look like this. All coming from a single common ancestor, all related to one another. There's only one way to draw an unrooted phylogeny for multiple, for 3 species. If there's more than 3, then you can do multiple unrooted phylogenies, but the number is less than rooted phylogenies. So there we go. Now I can think about this. I could put D along any one of these branches. So I could put D here, and that would say D is most closely related to C. I could put D right here, that D is most closely related to B, and I could put it here, most closely related to A. And I've actually left out a couple possibilities because rooted gives me more possibilities. So let's jump back, put B back up here, and let's just draw a rooted phylogeny and realize this is one of only 3 rooted phylogenies. We looked at 2 others, right? There were 3 possible ones. And so realize that I could put D along any of these branches. I can put D here, most closely related to A and C together. I could put D here, most closely related to all of them together. I could put D here, right? So along any of these branches, I could add D, and that's a different phylogeny. And then when I include the other 3, it grows exponentially. So it turns out that I've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 different possibilities times 3. So if there are 4, then suddenly I have I believe some of them are redundant. I think the number is 12. But anyway, it's somewhere in that neighborhood. There are 12 different ways to write a rooted phylogeny if there are 4. And we won't keep going on. It's going to get trickier and trickier, and this number is going to get big. Now, the key is, as this grows exponentially, as we add species taxa to our analysis, the number of possible phylogenies that we would need to evaluate and estimate grows exponentially. And we're only trying to find one of those. We're trying to find the true one, the very best one, right? But it becomes a very big problem very quickly. In fact, this type of problem, it's one of many problems that we call NP-complete. That's a class of mathematical problems that the solutions, the number of solution grows exponentially and gets so big so fast that we cannot do an exhaustive search once we have a reasonably sized data set. So by the time I get to something like, I think it's like 70 taxa, 70 species, which really isn't that many if you think about all the species we have, there are more possible phylogenies to evaluate than there are atoms in the visible universe. It's this massive, massive number, like 10 to the 80th power of different trees that we would need to evaluate. So mathematically, this is how we represent that exponential growth, where n is the number of trees, and factorials, if you don't know factorials, that's fine. We don't need to know this. I'm not going to ask you to calculate it. I do want you to underestimate. So here it is. Oh, there were 15. I was right the first time. So there were 15 rooted trees if we have 4 species, 105. But notice this number grows exponentially. By the time we get to 10, we have, what is that, 34 million trees? Again, by the time we get to, I think maybe it's 50 or 70, we have more possible trees than there are in the atoms in the visible universe. So it's a huge, huge, huge number. And basically, I put my little atom here to remind me of that. So basically, the idea is that we cannot solve it, even with our fastest supercomputers. It would take billions and billions of years to evaluate every single possible phylogeny, just because the number is so huge. Okay? And so that will come up later when we talk about how do we find the very best phylogeny if we can't search every single possible phylogeny. But for now, just know that it grows exponentially. It grows exponentially very, very quickly, and it falls into a category of problems called NP-complete. I'm going to put that here just because sometimes. And if you want to look it up, there are other problems that fall into this category also, and they're a subcategory under mathematics and computer science and your heuristics of how we solve certain problems. But it's an example of an NP-complete problem, because it gets so big so fast that there's no way to do an exhaustive search to be 100% certain that we found the best overall solution. And we'll talk in the coming chapters about what I mean by the best phylogeny.